All right. And so like I mentioned, was this section 42, right? Yeah, section 42. So a couple things about this graph theory. Has anyone, so everyone has gone through section 42? Okay, I see some hedging. Okay, I know Lauren, you haven't got yet. That's okay. Those of you guys who have gone through 42, Lauren, you haven't really, like, have you just started it, right? Or just,
No, I haven't started it
okay.
yet.
Okay, so a lot of this stuff will be new to you. For the rest of
Yeah.
Jenny and Andy, this will mostly be kind of review stuff. So if you guys have specific questions, like especially things like, oh, we got to this part, like I want to ask questions about that, definitely ask that today. But I will say is that going into we're going to skip section 43 and go into 44. So like neural networks and stuff. Um, I will say technically graphs, like a neural network is going to be using graphs, but we're never going to really talk about graphs in that same way from graph theory. So graph theory is really going to be, I mean, it really came out as a mathematical topic, and kind of like it's actually really good, useful thing in computer science. So in computer science, you might talk a lot about graphs and traversals and stuff. And so by proxy, because as data scientists, we have to be kind of computer scientists by nature, we're going to learn some of this information, right, about graph theory and stuff. But I will say is that it's not like the most common thing that you're going to be doing all the time. It's useful to understand how graphs work and like what kind of things are available there, but you likely will not, like for example, going into like an interview, like for a data science position, you likely will not be asked to like talk about graphs in any way, like unless it's a very specific thing to what they're doing. So for example, we'll find that Google uses an algorithm called PageRank that they developed to determine, like what websites they can go to. If you were going to Google and they're on search, they'll probably, like, I mean, I don't know, probably, I don't know anyone who's actually done this position, but like if you're looking for a search position in Google, they probably are expecting you to be at least familiar with graphs and stuff like that, and like the idea of their algorithm. But as a general data science question, probably not. They might ask you a computer science question, might involve graphs, but they're likely not specifically looking for graphs. So hopefully that kind of gives you a little primer of like why, we're talking about this, and why also don't stress about it too much, in my opinion. But it will be useful for, in particular, when we talk about natural language processing with something like hidden Markov models. Markov models uses graph theory, but it's not going to be something where, I mean, if you never heard graph theory and you did Markov models, you probably would understand it perfectly fine. So just kind of put some context in there. But okay, so let me go ahead and share my screen. And these are going to be more high level concepts and stuff. But if you guys want to ask more questions about it, definitely just ask them as you come up with them. So here is my little notebook here. You guys can see that. What is a graph and all that? Cool. All right. Let me grab your guys' window so I can see you guys'. All right, cool. You guys are all nodding. All right. So first thing is like, what is a graph, right? So as you guys have gone through this, it'll be kind of obvious, but like a big thing, like what graphs are, when we talk about a graph mathematically, we're not talking about plots, right? So we've been talking about graphs, like plotting and everything like that, but it's going to be a completely different entity. So if you had that kind of mental hang up, just kind of know is that like when we say a graph, we're not talking about a plot and everything like that. Okay. So the real reason, like I kind of make a joke, is that like computer scientists are really uncreative and like just name things really horrible. Again, I respect computer scientists, mathematicians, and everything like that. But if anyone who's worse than like computer scientists, it's probably math people. They take the same word and then like they use it for a new context. And so graphs are really going to be like this new thing. So again, when we say a graph, it's a mathematical object, and it's going to be something called vertices and nodes. Note that I will kind of go back and forth. My background is more mathematics, so I'll tend to say vertices. If you're in more computer science background, you might say nodes, but they mean the same thing in this context. Okay, and they'll be connected together by edges. Okay, so these are kind of formal terms: edges, vertices, nodes. And just note that graphs basically put emphasis to relationships. So this is very different from like tabular data, because tabular data, which think like a table, right, pandas, and like a data frame, right, is they're talking about like, okay, here's this instance and here's the properties of that instance, right, this data point. A graph is more emphasis saying, okay, the points themselves are important, but how do they relate to each other? And that's where graphs are really, really great at, is that they're really emphasizing these relationships. So kind of a quick kind of like idea of like if you guys what graphs are. When was a good, what kind of problems, what kind of concepts would be good to use graphs in? Feel free to chime in. When would graphs, when at least, you can talk about from the curriculum, Andy and Jenny too. So.
Anything that's about relationships, it's good for that. Like social networks, for instance.
Social networks, yeah, good, great. So social networks, right? Social graphs, right? Basically like how, if imagine like Facebook, if you're friends to someone, right, going through, you can also have social networks where the connections are based on how many interactions, how many direct messages you send to someone and stuff like that. Any other ways we can think of graphs and stuff like that? Like what kind of problems would be useful?
I mean, another one in the curriculum was recommendation systems.
Yeah. So recommendation systems is an interesting one. There's a lot of work. I was kind of looking at a little bit of what other people have done. To be quite honest, I haven't seen too much recommendation systems done directly with graphs in the wild, mostly because there's a lot of other ways to kind of build this up. So we saw like singular value decompositions of SVD from section, 41. We'll also mention about embeddings, which we haven't really talked about how you build embeddings other than like SVD, but you can also build embeddings through neural networks and stuff like that. And so I think graphs is an interesting one. I think the one reason why you don't see too much of it is because graphs tend to be a very hard mathematical object to deal with. Has anyone, this is kind of going a little off topic from here, but has anyone heard of like topology, like as a mathematical term? Okay, see Jenny kind of get nods. This is where I have my book here because I was looking through and stuff like this. This is an undergrad textbook. So this is like topology right here. And so like there's a common one, like you can see like this is a really famous problem where you have two interconnected links and you can transform it to something that's basically not interconnected. And so this right here, which looks very organic, like you can kind of move and stretch things, looks very like organic and like kind of like not very like rigid like you would think in mathematics. And this is a really interesting mathematical topic that you try to put formalism in there, and there's a whole lot of stuff out there where like we're not really sure if you can do this stuff. That topology comes off of graph theory, or at least has some kind of connection between that, and they have similar like it can sometimes be a little tough to mathematically determine certain aspects. But anyway, graphs can actually be very useful for other things too. But recommendation systems, I would say, is that there have been some research, like I was looking at a couple papers that had come up with graph theories to build up its relationships. But usually those can get really tough because it's like, how exactly do you formalize this other than basically try to go through it, what's it called? Like you have to build up the structure well to pull something out of it versus for SVD, you can already have the tabular data and pull out that information with those matrices. So, but no, great example. So a couple other ideas too is because of relationships. Classic, like we said, the social networks. Other ones are like, traveling, like Google Maps and stuff like this, So you can imagine like, oh, we have different cities or different waypoints and we want to connect these two, but they're only connected in certain ways. So in this case, the roads are the relationships themselves. So this can also be useful as well. Okay, so anyway. So kind of building up a graph. So we've talked about these things, but we haven't really seen any pictures of this. So it's kind of good to see like what a picture looks like. This is a graph right here. We'll talk about different types of graphs and things, but the main parts of a graph, which makes a graph, is that we have a node or vertices, and they represent the entity by points. So like each of these green circles right here is a single entity. And so you can say that each of those are those nodes or vertices. We also have edges, which are basically these lines right here connecting the different nodes and vertices, right? And note that I have a little couple notes here. For example, vertices are adjacent when they share the same edge. So you imagine like this vertex and this vertex, right, are adjacent to each other because you can connect them because they have the same the same edge. Okay, versus this vertex and this vertex wouldn't be adjacent because you can't directly connect them, right? If you imagine this, I like to think of it like traversal. So like you can imagine this is point A, point B, point C. Or if you think of like town A, town B, town C, these are the only roads connecting them. So you can technically get from, let's say you can travel, both ways, either way, back and forth. You can travel from A to B to C and get to C, but they're not adjacent to each other because you have to go through B. Make sense? Okay. Now, one thing about edges, you can also have adjacent edges. So adjacent edges are basically the same thing as adjacent vertex. They basically, edges are adjacent to each other if they share the same vertex. So you can see this vertex right here, this vertex right here, both share this edge here. Okay, so just know, I'm giving you guys some extra terminology. I don't think the curriculum necessarily talks about this, but in this case, when you see other, things talk about graphs and stuff like that, you're familiar with the terminology. And there's one other part in here, which edges can be weighted. So I'll kind of say right here is that usually when you picture graphs like this, you can think of it like you can pull on like, the different nodes and like push in and kind of move it around different spots, and they're equivalent to each other. So for example, like if I were to draw out a quick little graph of like 3 nodes and 3 vertices, okay? Or I'll put it like this. So like you can see like this graph and let's say this graph are equivalent to each other. Okay, at least in the way that I drew them. There's no distinction. I can kind of move it around and stuff like this. However, we can do something like we can put weight in here. So what this weight's going to represent, I usually think of it as like distance. So if imagine if like I put this like, oh, this is going to be a weight of 4 and this is a weight of like 1. The idea here is that there's a smaller distance from here to here versus this one. So usually here at weight versus distance, but you can think of it like distance, like, oh, how far away this is. In that case, this is just an abstract object. So if I labeled it like 1 and 4, right, I could have just labeled it like this too, and that would be the same thing. It's one of those things like if you remember back like on standardized tests, like, this image is not drawn up to scale. Same idea with graphs. In all math, basically you say it's never like to scale. Like you always assume that they're equal unless it's something else. So anyway, that's where we can have weights and stuff like that. Okay. Cool. Another quick note is that I think the curriculum talks about this, but a graph is connected when all vertices can be traversed via the given edges. So basically it means we can visit each town in some way, even if it means that we have to drive all the way over. If I had like another node right here that's connected like this would not be a connected graph because there's no way to get to this node over here. Of course, if I make just one small connection, also now it's a connected graph. Okay, and there's other things like, there's other ways we can talk about graphs, like certain types of graphs, like a planar graph and fully connected graphs. A fully connected graph is that every node is connected with every other node. So you can see like this node connects to this one, and this one, and then this node would connect to each one of them. So that would be a fully connected graph. So sometimes you'll hear that too. But it just means that basically you can get to any town by just traveling on one road. You don't have to go through multiple roads to get to the next town. Okay. Any questions on nodes, edges, connectedness, these definitions? Sound pretty understandable? Yeah. And it's like slow drawing, right? So cool. All right. So this brings us to the next type of graph, which is directed and undirected. So this is actually something called an undirected graph, and we'll kind of get that specification. So I'll keep using the metaphors like traveling along roads and stuff, because I think that's the most like familiar for us. At least in my opinion, is that you can kind of think of a directed graph as basically a one-way road. So basically all the edges have some direction. So you can only travel in one direction from one to the next. So you can see this little arrow here, and these are from like the curriculum, right? So like, for example, if we have Bob to Sally, right? Bob can only move to Sally in this direction, but Sally cannot move to Bob, right? So you can see that basically it's a one-way road. Note that we also say these edges are oriented, right? So again, something that going through, and sometimes these edges are referred to as arcs when they're oriented, when they have a direction. A lot of times I still hear people use, what's it called? Just edges. Then they understand that these edges just have direction. This tends to be a little more mathematical, I think, is that, well, in mathematics, you might specify saying an arc. Note that even though we have this edge going in one direction, there's no reason we can have a second edge that goes in the secondary, in the other direction. So if Bob can go to Sally, but Sally can't go to Bob, we can make a new edge, right? With a new arrow. And in that case here, we have it can go either way, right? Note that because we can have different weights, we can also make this like 4, and then maybe like this is like 10. So for example, it takes longer for Sally to get to Bob. There's only a one-way road that goes this way, and it's like this long looping thing. So note that these edges can have potentially, even though they point to the same, like they go back and forth, they can have different weights too. Okay, does that make sense? Now, if every edge, I'm not going to draw every single one, but if every edge, oh, well, okay, this is sometimes a shortcut. You can see here, so it goes back and forth. So you can have edge like this. But if every vertex, and every edge can be traversed one direction, the other direction in equal amounts, so same weight, we have something called an undirected graph. And so an undirected graph is just usually represented in the sense that we just have a single line, no arrows. So if you ever see basically with no arrows, it means an undirected graph. If you see arrows, you have to now consider that there are only certain paths you can take. Okay, cool. Any questions on all so far? Pretty understandable, right? Like, I think like for the most part, we're pretty visual where we'll understand like where everything's going through. So the next part is something called a path. So a path is relatively simple to understand. It's essentially just a sequence of nodes that we can travel going through. So like mathematically speaking, right, I can say a path is a sequence of nodes such that each node is adjacent to the node next to it, right? Which basically just means, can you get to, a path is describing how I move. So I go to Sally to, from Sally to Bob, to Jen, to Kate, to Bob, to Sally, to Jen, to Jake. That would be a path, right? And usually you represent it with the nodes themselves. And it's, you might have to specify the edges if there's multiple edges, but the point is that you can go through here. Note that in this graph right here, a path would be like Bob to Jen to Sally would be a path. However, Sally to Bob would not be a path that you can write out because there is no edge that can be directed towards that. Okay, sound pretty simple, right? Yeah, cool. So there's a couple of definitions here that you might see. A simple path is just a path where there has no repeating nodes. So I said like Sally to Bob to Jen to Sally, like I'm kind of repeating things over and over again. So that would not be a simple path. Euler path, right? So think of like Euler's number. Euler did a whole bunch of things. But an Euler path is a path that traverses through all edges of a connected graph. So in that case, you might have like from Sally to Bob, to Kate, to Jen, to Doug, right? To Bob, I guess, and to Jen, to Jake. So that could be an Euler path where you're going through all of the different edges. I'm sorry, you're going through all of the, not the, I said, I was giving the example versus, but all the edges. So going from Bob, Sally, Jen, going through all of these points. So you might have seen those things like where you like draw and like never lift your hand up. It'd be something like that. Okay, cool. All right, a couple other things, circuits, cycles, and loops. Okay, so a circuit is just a path whose beginning is the beginning and end are the same. So I go from Bob to Jen to Sally to Bob again. That would be a circuit. Okay, a cycle though is a circuit with no repeating vertices. So I could have done, for example, trying to think of a good example real quick, but like let's say Bob to Doug to Jen to Kate to Bob to Jen to Sally to Bob. That would be a circuit, but not a cycle. So simple enough. And then a loop, which we haven't seen yet, it's just a path with one edge that connects the same vertex. So usually you'll see something that looks something like this. Oops. Here we go, like this. Okay. And so if you had a directed graph, you would have something like some arrow like this. And this could also have a weight. Okay. So this is actually really useful. We'll see this again when we talk about Markov models. We can have something like not just what's called like different people or different cities. You can also have different states. So if imagine like a little, like, let's say like a little robot vacuum, like a Roomba. You have this little Roomba. What it can do, it can either, you know, like go charge at its station. You guys all know what Roombas look like, right? So they can charge at a station. They can either be cleaning the house, right? What else can Roombas do? I don't know. Just travel and sit there.
They can get stuck.
Yeah, they get stuck. Okay. I'll just put sit there, like they purposely sit there, just to kind of put things through, right? So what's kind of interesting, you can start making this relationship. Okay, we can either charge, we can clean, and then we can sit, and then we can actually connect these together. So for example, we can go from cleaning to charging, right? And we can probably go to charging to cleaning, right? We can also go from cleaning to sitting, charging to sitting. Oh, I guess I'm going to say that's nothing because if you charge, right, you're just sitting there. But you could go from sitting to charging, right? So you can kind of see like a little bit of like different things you can do. But you can also do the clean to clean, right? So you just continue to clean, and you can also continue to sit, and you can also continue to charge. And then what your weights could be something like, you know, if you have like, let's say 100% power, right? This could be something like, okay, when you charge, this is going to, you know, plus 100, right? Or something like that. It could be like plus 50 or something. So maybe every time step. If you sit here, maybe it's like minus like 5, like you lose 5 hours. But if you clean, you get like minus like 20, right? And so you can kind of imagine here, if I go to charge to clean, maybe that's like 0. So it doesn't really do anything. And this will be, let's see, I don't know, this would be like, let's say minus 10 because it's got to get there. So like, they're like different like paths and stuff like this. And this way you can kind of represent paths of states of saying, you can like, okay, like what should you do next kind of deal. And so you can kind of figure out paths of like describing what this, you know, little Roomba is doing. So this is another way to kind of represent these different paths to, or this very abstract object with something that describes, you know, relationship. Like it's not about the actual destinations here. It's about what is it doing and what can it do next. Okay, cool. Cool. So let's see here. All right, I think that's everything on here that I've talked about. Any questions about this? I think it's all pretty understandable, right? Yeah. Okay. So just real quick, I did want to mention about adjacency matrices. So I don't think the curriculum talks it. For Andy and Jenny, okay, I see some head shakes, so no. Yeah, so adjacency matrices are a nice way to represent the relationships of this graph in a matrix form. So you'll commonly see this. So for example, you can see, I pulled this up from, I think Wikipedia here, but you can see an undirected graph, a directed graph, also a weighted graph. So note that undirected graphs and directed graphs, we can just say there's a weight of 1 for each one because it doesn't really matter since they're all the same. So an undirected graph, you'll notice that it's symmetric along the axis here, which makes sense. If you can travel from B to A and A to B, that means they're connected here. So you can see A and B have 1, and then B to A has 1. And you can see like the different parts here. So this kind of shows you a little bit like, for example, A is very connected. We have B, C, D, E, A, because basically you can see it's very connected. It's not connected to G. Okay, makes sense. Cool. All right, then we also have directed graphs. You can see obviously that they're going to be unsymmetric, right? Because they can only go in one way. In this case, this graph can only go in one direction, right? So from A to B to C, there's no like going backwards. But if I had something like, if I had like a little path that went from like E to like A, like that, right? Then we would have something where we actually have E connects to A, and this would be 1. Okay, but note that it doesn't have to be symmetric because they're only one direction. Okay, cool. And then you can see weighted here. It's the same idea as either of these two. In this case, it's undirected, but they're just connecting with numbers. So you have these actual numbers in here. All right, cool. Simple enough, right? So this can be really useful in a lot of mathematical terms and stuff like this, adjacency forms. So if you ever look up more graph theory, especially relationships and stuff like this, you likely will bump into an adjacency matrix. All right. Awesome. Sound all good so far? Yeah, cool. Yeah, all right. So real quickly, I'm not going to go through all the uses because the curriculum goes through a whole bunch of it. But some use cases, I mentioned one that the curriculum hasn't mentioned yet is hidden Markov models. So that will be really useful in natural language processing, especially because we can actually build up like essentially sentences and stuff like this and saying, you know, what this next predicted word is going to be. So they're very relatively simple to construct, but they can be they basically are represented with graphs, and we can then build up, you know, something that seems more human, like essentially more human, more understandable. So we can start building structure with that case. So this is really useful in natural language processing. But in other ways that the curriculum talks about are like path searching. So we can figure out, you know, what kind of paths, for example, a typical one is like thinking of the shortest path. Like you think of like, you know, GPS, but like Google Maps, you might look for like the shortest path. Also note that also might just mean not the shortest distance, but also the shortest amount of time. So there's different ways you can find this. Famous problems of this is like the traveling salesman, PageRank, which is by Google and stuff like this. I'm saying like where you can kind of get from one website to another part. And that's actually how they rank on whether a website is quote unquote more useful or should be ranked higher based on how much connections it goes, like how many times can you go through different websites to get to the other one. So these are interesting ones too. We also have connectedness and centrality. Basically, you can think of it as like the biggest influencer amongst the members. And influencer, I kind of got some weird terms now because social media influencer. But what I really mean by influencer is just mean like the thing that has the most connections. You guys ever play the game like, not the game, but well, there's a couple things. So like, you know, the 6 degrees of Kevin Bacon. You guys know that, right? And so if you guys haven't, has anyone not heard that by chance? Okay, Lauren, you haven't heard that before? Okay, so 6 degrees of Kevin Bacon, the idea is that you take something like an actor or an actress, right? And you start off with that person and you say, okay, like what movies have they been in, right? And you can say, okay, like, well, they've been in this movie with, you know, actor A, and this actor A has been in movies with actor B, and actor B has been in movies with Kevin Bacon. And the idea is that you can always trace an actor all the way back to Kevin Bacon within 6 essentially jumps. And so there's also this thing like with the small world hypothesis is that the whole human race is connected basically by just, I think 6 or 7, depends on, you know, who you ask exactly what that number is. The idea is like, if you know a person who knows a person who knows a person, you can get to anyone in the world. And the idea there, the reason why that exists is because there's certain people, whether they're actors or just people in general, that tend to have many, many connections. And so that one connection is a key point, is that if we lose that one key point, for example, like, you know, they get deleted from the graph, essentially, it's now a lot harder to get through. So this is where the idea of connectedness and centrality is that we're looking for that key person, essentially, that influencer amongst all the other parts. You can think of this also in social media, is that you have that like one friend that has like, you know, 2,000 friends, you know, and like, do you really have 2,000 friends, you know, kind of deal. But like the idea is that they're connected to a bunch of other people versus someone who might only have, you know, maybe they don't use Facebook or that often or something. They only have like 30 friends, right? So the idea there is that you have more connections in there. Okay. And then last one is clustering, which is a really interesting one. Basically, the idea here is finding subgroups. This tends to be a little bit hard mathematically to define. So this is definitely like an interesting problem of saying, you know, like, how do you break clusters up? And like the same way that we talk about like, not k-nearest neighbors, I always miss it, k-means, right? Saying like, you know, like clustering, saying, oh, what are different groups and stuff like that. So yeah, these are some uses that the curriculum talks about in particular. All right. Any kind of general questions about use cases or when graphs might be useful for us? Okay. Yeah, I'd say the overall thing is that graphs are going to basically be focused on relationships. If you can build it in a relationship, it might be useful to represent in a graph, okay?